This video covers center of mass. Up until now, we've treated everything as point particles, but we know that in real life that there is no such thing as point particles, that everything actually is spread out in several directions. Now, what can really happen though is we can calculate the center of mass, and this is the point that moves as though all the mass were concentrated there and all external forces were applied there. Okay? And I'll show you a couple examples of what that means. Another way to think about center of mass is an average of all the mass at a position. So average position of the mass. Okay, and we have several different ways to consider this. In one dimension, we just look at the x direction center of mass, or in the y direction or the z direction, but again, we're only looking at one of these directions. And in 2 or 3 directions, we start considering different more. Now, down here, we have a slightly different notation that we've seen before. This is called unit vector notation. All this means is that this I, J, and K just represent the direction that these numbers are going in. So down here, you have a 3 in the x direction, a 4 in the y direction, and a 7 in the z direction. Again, the I, J, and K don't actually represent anything. They're just telling you that these values that are in front of them are going in those directions. So over here, you can see a coordinate system where you would have 3, 4, and 7, and it's telling you that it's going in those 3 different directions. Okay. So this example shows a hatchet, and we know that a hatchet that's very similar to a hammer but with a blade has a heavier end on one side and a lighter handle on the other. Now, the center of mass is actually going to be located towards the heavier side of this hatchet. And if we look at just the center of mass, you can see that that particular center of mass travels at exactly the way that we've treated point particles. So, yes, we can see that the hatchet itself is rotating about that center of mass, but if we couldn't see the rest of that hatchet, then it would look like every other projectile that we've seen up until now. Now, the important part to stress here is that when we talk about the center of mass, we're talking about the position of a center of mass. So remember that we are calculating a position here. We are talking about units of meters in most cases. So x cm is a position of the center of mass, in this case, the x direction. M1 is representing the mass of our object in our object 1. Mass 2 is object 2. X1 is a position of our first object, and x2 is a position of the second object. And then capital M, the way we see it over here, is going to be the total mass of all the masses involved. So again, in shorthand, it is the summation of your mass times its x position, in this case, divided by your total mass. Okay. In order to see this spelled out, it would be mass 1 times position 1 plus mass 2 times position 2, all divided by mass 1 plus mass 2, and then several more if you had more objects. So this problem asks us to calculate the center of mass of the 3 particles. Now, here we're not given a coordinate system, so the easiest thing to do would be to create a coordinate system along one of our objects, because it makes some of our calculations a little bit easier. Now, you can see that none of them have any mass along the y-axis. All the centers lie along the x-axis. So the first one has a center of mass of 0, 0. The second one has a center of mass of 2, 0. And the third one has a center of mass of 5, 0. Now, to calculate the total center of mass, we need the sum of the mass times its x position all over total mass. So for the first object, my total mass was 0. My position was 0. For the second object, my position was 2. And the third object, my position is 5. So Even though the first object doesn't have a position in the x direction, it lies on 0, 0, we still consider it in our total mass. So here you should get a value of 2.57 meters. That means our total mass, or our center of mass, lies somewhere here. Actually, somewhere here. Now, the previous example was for only one dimension, in the x to be specific. If you have several objects and they do not lie on one axis, then you have to treat the center of mass in the x, y, and z direction separately. Once you have all three directions, all three center of masses, then you can combine them to find a vector center of mass. In this example, we are provided a coordinate system. Here you can see that each dot or each object will have both a x and y position. So let's start with given each of these objects their coordinates. So this one is 0, 4. And this one over here is 3, 1. Now, to find our center of mass in the x direction, we can do the same thing we did before. And for this part, we can pretend like they're all lie on the x-axis. So for my first object, it is 1 kilogram at position 0. Second object is 2 kilograms at position 3. All over 2 plus 1. So you should get a center of mass of 2 in the x direction. For my y direction, the sum of the mass times the y position all over total mass is equal to 1 times 4 plus 2 times 1 all over 2 plus 1. And that's also 2. And that's my center of mass in the y direction. Now, you can write your vector sum in unit vector notation. Or you can write your answer as a coordinate. So again, my center of mass is going to be located here at position 2, 2. In this example, you have 3 different masses with their vector positions written in unit vector notation. So again, I, j, and k don't mean anything. They just tell you that the numbers in front of them go in those particular directions. Now you can see from this first number that it doesn't even have a j. That means that its vector notation tells us that there is no coordinate in the j direction, so or in the y direction here. And if it makes you feel more comfortable so you can line these up and kind of visualize what we're looking at, then you can rewrite it with a 0 in the middle so that you can see all of these are in the x direction, all of these are in the y direction, and then all of the last numbers are in the z direction. So if you're asked to find the center of mass of this system, then it simply follows as the position of the center of mass in the x direction And again, for the x direction, we're only using the x coordinate system. So 3, -4, and 10. So this -0.94 is our position of our center of mass in the x direction. In the y direction, we use only the j values. Again, for the first one, we had that 0. And then for the z direction, you have -2, 7, and 10. So to calculate the center of mass, we only use those numbers. And then you can write your final answer in vector notation. Again, if this was in the x direction, it goes in front of your I. If this is in the y direction, it goes in front of the j. And if this is in the z direction, then it goes in front of the k. So those previous examples were still point particles, but they were located somewhere on a coordinate system, and we had to find our center of mass that was somewhere in between those 2 points. But again, we know that in real life that we have objects that have mass that go through its entire body, and that it varies throughout that position. So for objects that have a continuous mass distributions, you can find the center of mass by summing up all the little pieces of position vectors, multiply it by the differential of mass, and dividing by the total mass. Again, we still see our summation here, but again, because we're adding all these infinitely tiny pieces of mass together and multiplying them by their position vectors, then we have to use an integral symbol instead. So we know that if we look at a rod that is uniform in mass, meaning that it has the same mass distribution all the way through its length, then we can assume that the center of mass would be located right at the center. Okay. Here, we're going to prove it mathematically. So we want to show that the center of mass of a rod of mass m and length L lies between its ends, assuming the rod has a uniform mass per unit length. Again, what that means is that the same mass is located every unit of length along this rod. So down here we have Greek letter lambda that's going to represent our linear mass density. And in this particular case, we have our total mass of my object being divided by the total length of the rod. Again, this is true because it is a uniform mass per unit length. So that means that even if we have a small change in mass, that it's still going to be distributed over a change in x. So we can start with our equation. R cm, or xcm, because everything is lying along the x-axis, is equal to 1 over m times the integral of, I'll go ahead and use x here, x dm. Go ahead and replace r with x. Again, I'm using x in this case because all of my mass is being located along the x-axis. So going back to our linear mass density, our small change in m divided by our change in x, this can be rewritten as a change in mass is equal to my linear mass density times my change in x. That means wherever I see a change in m, I can replace that with a lambda dx. Now, here I can see that I have both an x and a dx. So I can take the integral of this, and this becomes 1 over m. In this case, my lambda is a constant, so I'm going to go ahead and pull that out. And this becomes x squared over 2. Now, this integral has to be evaluated by our limits of x. In this case, it is from 0 all the way to the end of the rod, length L. So when I evaluate that, I get lambda over m, L squared over 2 minus 0, or just lambda over m times L squared over 2. Now, I know a different value for lambda. Again, it was a constant in this case. So lambda can actually be replaced with m over L, our original description of a linear mass density. So with some algebra, this cleans up to L divided by 2. Again, we can see that our center of mass is located halfway through our length L of the rod. Now in this situation, we have a non-uniform rod. That means our mass is not going to be the same the entire way through. So suppose a rod is a non-uniform such that its mass per unit length varies linearly with x according to the expression lambda is equal to a times x, where a is a constant. Find the x-coordinate of the center of mass as a fraction of L. So we know that in our final answer, we have to have it in terms of L. So I can use xcm here, because again, all my mass is along the x-axis. 1 over m times the integral of x dm. Remember that our lambda is equal to our change in mass over change in position. So dm is equal to lambda times dx. But in this case, lambda is no longer a constant. So where we see dm, we're going to replace it with lambda dx. Lambda dx. And then again, my lambda is not a constant in this case, so we can replace lambda with our a times x. And here, a is a constant. So we get a over m times the integral of x squared dx. So the integral of x squared is x cubed over 3, and we're evaluating this from 0 to L. Cleaning all of that up, we get L cubed over 3. And it's actually a little bit better to put our numbers in front of our variables. If this function gives the position of the center of mass, then the first derivative gives the velocity of the center of mass. So the velocity of the center of mass would be my mass 1 times my velocity of that mass, plus mass 2 times the velocity of that mass, all divided by the total mass. This is also true for the total momentum of a system of particles. This is equal to the total mass multiplied by the velocity of the center of mass, which is basically this equation rearranged. Again, if I rewrote this as my total mass, m, times my velocity of my center of mass, then this would be equal to the sum of my individual momenta. So our last statement had a few implications. This tells us that the sum of the external forces is going to be equal to our sum of our total mass of the system times our acceleration of the center of mass. So again, this looks very similar to just F equals ma, but here we're specifically talking about the sum of the external forces. That means if we have two people on a frictionless surface and they push on each other, that is not considered an external force because the force that's coming in between them is included in the system. So, what if the total external force is zero, meaning that there are only internal forces acting here? Well, then that means that the acceleration of the center of mass is zero, meaning that our center of mass would be constant. Now, the center of mass is constant at the beginning, then the center of mass remains zero, which means that the center of mass does not move. So, these two people who are on a frictionless surface, if they were to push on each other and one would go in one direction because of conservation of momentum, and the other person would go off in the other direction, the velocity of their center of mass would actually remain unchanged and would not move.